What's up, everyone? Welcome back to the Math Corner. Today, we'll be learning about logarithms and hyperbolic trig. So let's get started. So what are logarithms? Logarithms undo exponents. If I have a to the b power equals c, I can rewrite this as log base a of c equals b. I can rewrite this equation to look something like this. Logarithms are inverses of exponents. So if I have the function or the graph y equals a to the x, remember to find an inverse, we swap the x and y. So we'll get x equals a to the y. And then if you take the logarithm base with base a of both sides, you'll get log base a of x equals y. So basically, logarithms are inverses of exponents. On the calculator, you may just see log x. So when you see log without a base, it's the same thing as log base 10 of x. And if you see ln x, that's the same as natural log of x, which is basically log base e of x. Alright, so I'm going to go list out some properties of logarithms that are pretty important to know. So knowing that exponents and logarithms are inverses of each other, we can say that b to the log base b of x is equivalent to x. They undo each other. And same thing with log base b of b to the x. That's just the same as x because they undo each other. Log base r of ab, so r is just some other random constant. So log base r of ab is equal to log base r of a plus log base r of b. So you can split up products inside a logarithm to become basic addition and subtraction. Log base r of a divided by b is equal to log base r of a minus log base r of b. And so these are like the four identities that I'm able to fit on the screen, but I'm gonna clear out my screen, all right? And the fifth identity that I want to talk about is the change of base identity. So if I have a logarithm log base a to the c, log base a of c, I can rewrite that as log base r of c, where r is just a different number, divided by log base r of a. So I can change the bases if I have like a common base like r, and then I say log base c divided by log base a. So I can change this logarithm to any base that I want as long as I keep this. So those are just some of the important properties of logarithms that you need to know when going into calculus. All right, so let's explore what the graphs of logarithms look like. So all logarithms, if they've not been translated, they go to the point 1, 0. And what logarithms are is they're really just regular exponential functions reflected over the line y equals x. So here is an exponential function that I drew. It's not great, but it looks like one. All right. And if I have the line y equals x here, I can create an inverse function, which is basically a mirror on the line y equals x. And you see that this is what a logarithm looks like. This function at the bottom right over here is what a logarithm function looks like. Logarithms have this general shape, but they can look slightly different from each other based on what what the base of the logarithm is. So for example, if the logarithm has a higher base, you'll see that it has a sharper turn at 1, 0. Similar to how an exponent with a larger base will have a sharper turn like this. It will increase a lot more rapidly. So these are what logarithms look like. They can obviously be translated up, down, left, or right. You can have a negative logarithm. So for a logarithm which goes all the way up from here down like this. You can do anything with logarithms. Same you can do. You can transform any of your other functions. So yeah, these are what the graphs of logarithms look like. They're basically exponential functions reflected over the line y equals x. Logarithms have a vertical asymptote at x equals 0. So basically, exponential functions, they have a horizontal asymptote at y equals 0, right? So when you use the same logic with inverses, you can conclude that there's going to be a vertical asymptote at x equals 0 for logarithms. One more thing I wanted to cover before we move on to the next topic is domain and range for a logarithmic function. We know that an exponential function, I'm going to draw both an exponential function and a logarithmic function. We know that an exponential function has the domain -infinity to +infinity, and the range is from 0 to infinity, right? So whenever we have inverses, you can just flip the domain and range. So now the domain of a logarithmic function is from 0 to infinity, and the range of the logarithmic function is from -infinity to +infinity. The reason why we can't go below 0 is because it doesn't make sense to have a negative, if I have log base 10 of -5, that doesn't make sense, because what this is asking you for is how many times can you multiply, sorry, I'm not gonna write equals, it's asking how many times do you multiply 10 with itself to get -5, and that's just, it's not possible to do that with any real numbers. So this is why logarithms have a domain from 0 to infinity. All right, so let's explore what hyperbolic trig is. That's the second part of this video. So hyperbolic trig, they are a separate class of functions that behave very similar to normal trig functions, which is why we call them hyperbolic trig functions. So I'm going to go list out all the hyperbolic trig functions for you. So sinh x, that's how we pronounce it, is equal to e to the x. Remember, e is Euler's number. E to the x minus e to the -x divided by 2. Cosh x, that's how you pronounce cosh x, is e to the x plus e to the -x divided by 2. Tanh x is sinh x divided by cosh x. So this is this is very similar to how just regular tan x is sine x divided by cosine x. Tanh x is sinh x divided by cosh x. All right. Now we have a reciprocal hyperbolic trig functions, and these are pretty easy to guess. So for example, cosec x is basically just 1 over sinh x. Oh, sorry, I almost wrote just regular sine x. Sinh x. Sech x is 1 over cosh x. And sorry, not tanh. And cotang x is equivalent to 1 over tanh x, or cosh x over sinh x. So why do we use hyperbolic trig functions? Well, we use hyperbolic trig functions because they are found really commonly in nature and in physics. One example is if we have two poles like this and we hung a rope like that. I'm going to draw the rope in a different color so it looks nicer. And I hang a rope like this. Galileo thought that this was a parabola, but actually we later discovered that this is the hyperbolic trig function cosh x. So this is just one of many scenarios when we end up using hyperbolic trig functions to describe the real world. All right, so let's explore exactly how hyperbolic trig is, well, how these special classes of functions are related to hyperbola, how hyperbolic trig is related to hyperbola. So the thing is we have the function x squared minus y squared equals 1. We can parameterize this using hyperbolic trig. What I mean by parameterize is we can define this as a parametrically defined curve. So we can say that x of t is equivalent to cosh t, and y of t is equal to sinh t. All right? So we can label any point here, and the coordinates would be cosh A, sinh A. So point A has the coordinates cosh A and sinh A. Now it's even crazier is say I draw a line from this point to the origin, all right? And we're interested in this area bounded by the x-axis, the line from the origin to A, and the hyperbola until it intersects A. Take a guess on what this area is. Believe it or not, the area of this is A divided by 2. So this is, how hyperbolic trig so happens to relate to hyperbolas. Okay, so let's look into the symmetry of hyperbolic trig functions. I'm going to create two columns, even and odd. Sinh x is an odd function, the same way sine of x is an odd function. Cosh x is an even function, the same way cosine x is an even function. Tanh x is an odd function, the same way tangent x is an odd function. Cosec x is an odd function, the same way cosecant x is odd. Sec x is even, the same way, secant x is even. And last but not least, cotang x is odd, the same way cotangent x is odd. So basically, hyperbolic trig, they have the same symmetry as their corresponding, regular trig. So you don't have to memorize anything new. It's just these functions have the same symmetry. So cosine x, secant x are both even, just like cosh x and sec x. And sine x, tangent x, cosecant x, and cotangent x are all odd, the same way sinh x, tanh x, cosec x, and cotang x are odd. Okay, so what do hyperbolic trig functions look like? So I'll just draw some exponential functions for reference. Okay. This is half of e to the x, and this is half of e to the negative x. So coshax looks a little something like this. It's like a parabola, and it has sort of like two asymptotes, as you can imagine. It gets really, like, as you go closer and closer and closer to negative infinity, coshax approaches half of e to the negative x. And as you get closer and closer to positive infinity, coshax approaches half of e to the x. So that's what coshax looks like. All right, so as you can see here, I've drawn two exponential functions. I'm going to draw syntax afterwards, but right now I've drawn half of e to the negative x, negative half of e to the negative x, and this is half of e to the x. So what syntax looks like is it looks a little something like this. It almost looks like a tangent, regular tangent function, sinh x. The only difference is this is not periodic. This just follows, as you approach infinity, this function approaches, half of e to the x. And then as you approach negative infinity, the function approaches negative e to the x divided by 2. This one. So that's what sinh x looks like. So sinh x looks like a, I don't know, what do you call it? Like a, kind of like an S shape. I don't know if you can see it, but it kind of looks like an S shape. Tanh x looks like this. If this is y equals -1, and this is y equals 1, tanh x looks a little something like this. It looks very similar to arctangent of x. So basically, as you approach infinity, the function approaches 1, which is one of its horizontal asymptotes, right? And as you approach negative infinity, the function has another horizontal asymptote at y equals -1. Now, let's move on to sech x. Sech x, if you remember, is 1 over cosx. Sech x, the graph of sech x looks a little bit like a bell curve. It's like it gets really, really close to 0 when you get further away from x equals 0. So it looks a little something like this, a bell curve. As you get further and further away from x equals 0, the function gets closer and closer to 0. And at x equals 0, the function equals 1. So that's just 0, 1. And this is the graph. And this is the graph of sech x. Okay, so let's look at what cosech x looks like. Cosech x looks really similar to the function 1 over x. It just looks like a rational function with horizontal asymptote of y equals 0 and a vertical asymptote of x equals 0. And last but not least, we have cotangent x. So I'm going to go label the y axis again. Right? Cotangent x has two asymptotes. One at y equals 1 and one at y equals -1. Cotangent x looks like this. this is what cotangent looks like. So as you get closer and closer to infinity, cotangent x approaches, 1 from above. And as you get closer and closer to negative infinity, cotangent x approaches -1 from below. And then there's also a vertical asymptote at x equals 0. So yeah, this is just basically how to graph your hyperbolic trig functions. Okay, so let's look into some of the addition and subtraction identities. There's two main identities you want to learn here. So the first one is the sum of cosh x and sinh x. And dash is equal to e to the x. The difference between cosh x and sinh x, on the other hand, is equal to e to the negative x. Those are the two identities that you have to learn for addition or subtraction. Okay, so here's when things start getting a little bit tricky with identities. For Pythagorean identities, we know that sine squared x plus cosine squared x equals 1, right? But with hyperbolic trig functions, the signs are a little bit different. So, with hyperbolic trig, cosh squared x minus sinh squared x equals 1. It used to be a plus sign with like regular trig, but it's actually a minus sign here, all right? Then you also have cotangent squared x minus 1 equals cosec squared x. And then you got tangent squared x. Oh, that's tangent, just normal tangent. Tangent squared x minus 1 equals sec squared x. So here, like, these signs are a little bit different for the top one, for their main Pythagorean identity. And then in normal trig, it would be cosecant squared x minus 1 equals cotangent squared x. But in this case, cosecant and cotangent have swapped their places. And same thing with, tangent x and sec x. So for this identity, what I like to remember is you just subtract the sine sinh squared x, right? So cosh squared x minus sinh squared x equals 1. And then for these two identities, I just like to memorize that you just switch the original trig function. So instead of being cosecant squared x minus 1, it just becomes cotangent squared x minus 1 equals cosec squared x. And then tangent squared x minus 1 equals sec squared x. Okay, so let's explore some of our angle sum and difference identities. These are, again, really, really similar to the original trig functions. So let's look at sinh a plus b. That's equivalent to sinh a cosh b plus sinh b cosh a. Sinh a minus b is just equal to sinh a cosh b minus sinh b cosh a. Now the difference here is with cosine. With cosine a plus b, that was originally cosine a times cosine b minus sine a times sine b. Right? But now you're adding you're adding cosh a times cosh b with sinh a sinh b. All right, let me show you what that looks like. So cosh a plus b is equal to cosh a times cosh b plus sinh a times sinh b. So what I was talking about earlier is you used to, for regular trig, cosine a plus b is equal to cosine a times cosine b minus sine a times sine b. But here you're adding them, so that's the only difference. And let's see, cos a minus b is just equal to cos a times cos b minus sinh a times sinh b. So these are your angle sum and difference identities. These are really similar, except for the cosines, the second terms, signs are swapped from the original trig function. And this brings me to something called Osborne's rule, or whatever it's. I like to call it Osborne's rule of thumb. But basically, what it says is you have two hyperbolic trig sine terms multiplied with each other. You usually want to put a negative in front of it if you're comparing it to the original trig identity. So the original trig identity for cos squared x minus sin squared x equals 1 is sine squared x plus cosine squared x equals 1, right? So you put a negative sign a negative in front of sinh x when you're converting it into hyperbolic trig. And the same thing is here. I have a product of two sine terms, so I'm going to flip the sign from the original trig, from the original trig identity. So that's what's different. It's a rule of thumb. Whenever you see two sine terms be multiply each other, you're just going to make that term negative, or multiply that whole term with -1 when you're converting it from an original trig identity to a hyperbolic trig identity. And that's it. That's pretty much it. That's the last thing that you'll be talking about today. Hope you enjoyed this lesson. Please subscribe and like the video if you thought it was good. Bye bye.